Thanks, Yusuf, for the introduction. Yeah, my talk is about persistent homology and algebraic persistence, algebraic perspectives on persistence. There's going to be a second talk later this week by Michael Kerber covering computational aspects. And as you can see from the subtitle, what I'm going to focus on is an important property of what we compute in persistence, the persistence barcodes. And that property is that those barcodes are stable, which really means they tell us something. When we have data and we have some kind of uncertainty about the data or some inaccuracies, either that or sampling uncertainties, that we can still get some useful and meaningful information out of those persistence barcodes. Let me introduce with an example. So you might know this saying about topologists that they're the persons who can't differentiate between a donut and a coffee cup. So that's a very bad joke, and so we are here to fight against that joke. We are just going to have a closer look at the donut, and we recognize that there's something topologically happening here inside the donut, and that's not happening inside the coffee cup, or maybe something else is happening in the coffee cup, but it will be geometrically different. And we will capture that difference between the donut and the coffee cup using a mixture of geometry and topology, and that will be represented in the persistence barcode, so that in that sense the pure topologists would not be able to tell you the difference, but using persistent homology you can say what they have in common, but you can also say that they're actually different. So that will hopefully bring an end to this joke and to all other bad mathematical jokes. That's why we're here. So here's a very simple picture of the donut, just the atoms of the donut, if you want, or the crumbs. Someone had the donut already, and so the question is: so you can recognize. I can tell you that this is a donut, and you don't start laughing because somehow you see that this is kind of annular shape or donut shape. And maybe the reason why you recognize that is that you make connections in your mind and you fill gaps. So that's actually also a good way of approaching this question rigorously. How can you associate some topological information to this purely disconnected space? Right? You blow balls of a certain radius around each point, and you let this radius increase, and you see what happens to the topology of this union of balls. And now you see, if you grow the balls slightly, you will create, so the balls will start connecting, and they will also connect in funny ways, in non-trivial topological ways, creating one-dimensional cycles here. So you already see something not just in H0, which tells you something about the connected components, but you see something in H1 telling you something about, well, you would, in the end, you would hope to see a one-dimensional feature representing this circular shape. But you see something else. You see these small holes appearing here. That's maybe more the foam that you saw in the donut than the hole, the big hole in the donut itself. And so these holes are also very short-lived. If you increase the radius slightly, they will go away. So we say, this is why we talk about persistence, and persistence is kind of the lifespan of those features through this filtration of increasing topological spaces built by unions of balls. And those features we just saw on the previous slide, they have low persistence. They exist only over a short range of radii. And now we have another one appearing, and that has high persistence. That's actually the hole in the donut, and that means if there's a large range of different radii representing this hole before eventually it will also be killed, because it will be filled in as the balls grow big enough, as you can see here. Okay, so eventually everything dies and it will just be covered by huge balls, but the question is, what's the range and over which we see these features? And here's just the same thing again, only overlaid. You see simplicial complexes representing the homotopy type, because people often argue and we also do the computation with simplicial complexes, and this is a construction called alpha shapes or Delaunay complexes. They're built from the Delaunay triangulation, and they represent the same homotopy type as the union of balls, but they're purely combinatorial. So you can think of these constructions as either topological spaces, simplicial complexes, as you want. And you see the same things happening. In particular, you see the same holes that we saw before also represented here as one-dimensional cycles in a simplicial complex. Okay, so we just saw 4 steps. In fact, we have an infinite family of unions of balls, one for each possible radius, but let's just focus on this 4 selection of different spaces. And since I said we can represent these homotopy types by simplicial complexes, we also know that there's only a finite number of changes, even though the union of balls are all different, but the homotopy type that's behind them, if you're only interested in that, there's only a finite number of interesting things happening. Okay, so the 4 spaces again represented as complexes here on top. And on the bottom, I'm going to show you the persistence barcode. What is that? So this is a collection of intervals. Each interval corresponds to the lifespan of a feature. So the horizontal direction is geometric scale. This is the radius of the balls. The vertical direction is irrelevant. It's just I have to order things somehow. And I ordered the intervals according to their length, but that's just for presentation here. That's not a crucial piece of information. So how can you read off something from this persistence barcode? You look at one scale, for example, pick the 0.1 corresponding to the first complex, and you see that there are 5 intervals containing this value in the persistence barcode. And that means that there is a set of 5 cycles, 5 one-dimensional cycles here that generate, and each of those 5 cycles is associated to a bar, so 1 bar, 1 cycle, and the set of those cycles generate the homology group. So the corresponding homology, the corresponding homology classes give you a basis for the homology group. I should say we're working with homology with coefficients in a field, not integer or other coefficients, and that's very important in order to even have such a thing as a barcode, and we will come to that. Okay, so what else can we read off the barcode? Not just what happens at one scale, but maybe much more importantly, we can read off the barcode how 2 different scales are connected in any 2 different scales. So let's just pick as an example the 0.2 and 0.4. Maybe it's a bit boring in this example, but let me tell you anyway what's happening. These 2 values, there's only 1 bar containing both values, and that tells us, now we can look at the corresponding set of cycles, there's only 1. That gives us you a basis for the image of the map induced in homology by the inclusion between the 2 spaces. So you have an inclusion from the smaller into the larger one, including a linear map in homology. Remember, we're working with coefficients in the field, so homology is all vector spaces. We have a linear map going there, and the number of these bars is the rank of this linear map, and if you want the set of cycles corresponding to these bars gives you basis for the image or the co-image of this map. So this is really what's persistent between 2 different scales. Okay, so that's the information that sits in the barcode, and it's very important from a stability perspective, it's very important to have this information being able to connect different scales, because anything that happens, as you already see from this picture, anything that happens at one single scale is very unstable. But when you're able to relate one scale to another scale that's a bit far off, and then what you still see at both scales must be stable, and there's theorems making precise what I mean by that we will see later in the talk. Just to summarize the formal settings that I'm going to work with. So what we have seen here, I call persistent homology, is nothing but the homology of a filtration, and I want to use a little bit of language of functors. So I consider a filtration as a diagram of topological spaces that's indexed by the real numbers, and the real numbers seen as a poset category. And specifically, that means I have one topological space at each real number t, at each index. And whenever I have two indices, as we have seen already before, then there's a unique inclusion map. That's why it's called a filtration, that these maps will all be inclusions, connecting smaller to larger indices. And those all those maps will be compatible with composition and identity, as you expect from a functor. So that's the formal way of saying what we have seen before. So this is how I interpret a filtration. And then I apply homology with coefficients in a field. Usually, like the most popular choice here is C2, because this is only a yes or no. And many things that you want to do in practice, you can already do with C2, but you can also use other fields. And so you apply homology, which is a functor from topological spaces to vector spaces. And so the persistent homology is a diagram from the reals to vector spaces, diagram of vector spaces indexed over the reals, and we call such a diagram a persistence module. Okay, so this is, and since we're going to talk about algebraic aspects, we're going to focus a little bit in this session today on the aspects of these persistence modules. Not so much the fact that they come from topology, but we're really interested in their structure. But we always have this motivation in mind. Okay, let me start by showing first motivating application of persistent homology, which also leads to the notion of interleavings, which will be important in studying persistence modules. So the question is really what you have seen on the first slide, the donut and the crumbs, and how can you guess that that's actually a donut, homology inference. You want to infer the homology of a shape. By shape, I mean a subset of some Euclidean space. And I want to infer the homology from an appropriate finite sample. So that's the problem here. I have a finite sample P of some shape that I don't know. I only know the sample. And the problem of homology inference is to determine the homology of the shape, omega, from the sample P, right? And now you could ask for a slightly more, a little bit more than just that. You may want to attack this problem not just algebraically, but you want to have a space. You want to somehow connect. That's what we actually have done with the union of balls. We want to construct a shape X that has the same homology as the unknown space omega. And that's what we have done before by approximating the shape by a thickening. And somehow the idea is to thicken enough so that the thickening, this union of delta balls around the points P, cover your space omega. And then that's also maybe an important aspect to point out. We don't just want an arbitrary isomorphism, but we want an isomorphism that's induced by some map, some canonical map. And here we would have, since the balls cover omega, we would have the inclusion of omega into these balls. And the isomorphism in homology should be induced by that map. That's a natural thing to ask for. I mean, so that's the idea. And that's a very natural idea, but it's subtle, it works, but only under rather strong assumptions. I mean, here's a theorem that tells you how you can achieve this goal. Yeah?
Maybe a question, how channel is shaped by copy? So far it's just a set, so could it be a fractal or?
Yeah, I mean, that's exactly the point of the next slide. And that's a reason why we want to reconsider that, because, I mean, I don't know how well, how far you can push the problem of homological reconstruction, for example, if you assume nothing. But of course, the question will come up in the sampling conditions. What conditions do you set on P so that you can actually solve this problem? And so let me show you one theorem that gives a partial answer to this by Ulrich, Smale, and Weinberger in 2006. So they have a solution to this problem for the case where you have a submanifold. So omega is now M, a submanifold of some Euclidean space, and we choose the sample P and this radius delta, such that one we always want to have. Sorry, this should be m. So the balls should cover the manifold, and then the radius should be below a certain geometric quantity. This is the reach. This is the distance that ensures that you have a unique nearest neighbor to the manifold in space. When you're closer than that distance in R to the D, then the projection is unique. So it's a quantity that's related to curvature, but also how near different parts of the manifold come to each other. And under these assumptions, you can actually recover. You can actually get a homology reconstruction. You thicken not by delta, but by 2 delta, and that gets rid of all everything that might go wrong in this B delta. So you might see these small holes that we saw on one of the first slides, but they will be gone when you thicken to 2 delta, and you get something that's actually homologically equivalent. Here's an example of something that does not work for this theorem. So here's a curve in the plane, and here's a sample. It doesn't look too bad. You can still recognize what the curve should be, or at least you can imagine that someone might believe that this is what we have seen before. Here's the barcode, the persistence barcode for the union of balls filtration. And let's just sweep through these different unions of balls and see what happens. So we have to increase the radius until things connect. It's still not connected everywhere. Now it's connected. And we have these small artifacts here. So here in the barcode, you can see the artifacts as represented by short bars. And so we just need to increase the radius slightly to get rid of them, but every time we get rid of one of them, we hit another problem. And if you look at the barcode, you can see that there's no choice of radius where you would have just the feature that you want, which is this red bar at the top. This is what you would like to see. And if you would want to make this work here, then you would need to find a value here for the radius that hits only the long bar but no short bars. And we see in these examples there is no such value. So, which also means that the assumptions of the theorem are not satisfied, but that's maybe not as obvious to see as verifying that something goes wrong in homology also. So that's a point where when you talk about persistent homology, it's really not just we look at the homology of a filtration and we just choose the right scale. We have to consider the whole thing together, because something else you see here is all these artifacts are short and this feature is long, right? And that was our initial motivation. So there's still some hope that can save this problem. Maybe not by asking for homological reconstruction, but for something weaker. But the information seems to be there, and we also saw from the point cloud it looked like a curve, so it should be possible to recover. And so that's actually true, and we can look at this other theorem by David Cohen-Steiner, Herbert Edelsbrunner, and John Harrer, which considers the persistent case, and the assumptions are similar to before. We have a shape omega, we have a sample. We need radius delta such that the balls cover the omega, and then instead of the geometric condition on the reach, here we have a condition on homology. We consider these inclusions of, so this is inclusions of the shape into thickening. So it's again kind of regularity of the shape itself, which maybe also answers your questions about fractals. That would be hard to satisfy for fractals, but if you have a shape that's regular enough and your delta is small enough, then thickening the shape will not change the homology. And so that's what I mean by inclusions preserve homology. The induced map in homology is an isomorphism. And if you have these assumptions satisfied, then the homology of the unknown space is actually the image of the map induced by inclusion of the smaller into the larger thickening. So you can see this example here. There's a dark shaded union of balls in the middle, and then there's the light shaded union of balls covering it. And it's maybe easier to, so you see that the dark shaded guy actually has two holes. One, one is the big one here, and then there's a small one here. And only one survives. The small one is filled in, and the big one is still there. And even though the big one also has problems, as we have seen before, there's 3 holes in the big one. But if you look at the barcode, and we look at the 2 radii corresponding to these 2 thickenings, there's only one interval hitting both. So that's the one feature that we want to see. This is this is exactly the cycle that can be represented by this, by the curve itself that we started with. So let me maybe I haven't mentioned this, by the way, but here's the URL for the slides, and I want to switch to the board now and give you a proof for this theorem, and it's a very simple proof. So we start by writing down the assumptions. We have the shape omega, omega thickened by delta, and then we have another thickening by 2 delta, and we assume that the union of balls, I think I need this still. I would, yeah, don't worry. So I assume that the union of delta balls around P covers omega, so there's an inclusion here. And I also assume that P is itself contained in omega, so there's an inclusion here. And then I go to 2 delta here, and I have inclusions from this union of balls around omega in union of larger balls around P. So I have this commuting diagram. There's also maps here. And then I pass to homology everywhere. So let me just put homology once here. You know, everything is happening in homology now. And then we have an isomorphism here and an isomorphism here, right? And that means this map is epi, this is mono. Okay, so this means we have a map. This is also an inclusion-induced map that factors through some that has a epi mono splitting, which means this guy here is isomorphic to the image of, let's call this map P, and then this the homology of this union of balls, the delta thickening of the shape omega, is isomorphic to the image of P, which also gives us a epimonofactorization. So you have the theorem already. This is isomorphic to this. This is isomorphic to this by assumption. So that's only, yeah? Okay, sorry. Yeah. So that will make it. Can you read it with the projector? Yeah. Okay. Okay. So that's all you need to prove that this works. It's a very simple argument, but it illustrates how important it is to know how to connect to different scales in homology, and what else it illustrates that will be important very soon is there's a hidden concept here. We're going zigzag between omega and P, and this idea of connecting 2 different filtrations in this zigzag way is something we call an interleaving, and that will be that will become interesting in a moment. Okay, so that's homology inference using persistence. Now let me move on to stability. By the way, I should take a break in 15 minutes, right? Yeah, okay. Okay, so stability, as I said, is a very fundamental theorem about persistent homology. And the idea is this: let's say we have two functions, and we consider the sublevel sets of these functions. What you have seen before, the union of balls is a special case of that, because the union of balls around a point set P with radius delta is nothing but the delta sublevel set of the distance function. Okay? So this is just a slightly more general case of what we have seen before. The function was the distance function, but you can phrase the problem in a more general way, and considering sublevel sets of arbitrary functions, and we want to study the persistent homology of those sublevel sets. And the theorem here says, if we have two functions that are delta apart in the supremum norm, then there exists a matching between the intervals of the barcode. Let me show you how the matching should look like. So let's say blue is the barcode of the function f and red is the barcode of the function g. And then you should be able to match the bars such that either that you match two intervals together, then they are similar, have similar endpoints. And some of them might be unmatched, and that means that their length must be short. It must be at most 2 delta. So let me give you some illustration here. Let's say we have the function so this could be the function f and another function nearby, but maybe slightly more complicated. So this is the function g. The L infinity distance is not too large. Yeah, here is the maximum distance between two function values. And let's draw the barcodes for the sublevel sets. There's only H0 can be non-trivial, so we look at connected components of sublevel sets. We sweep, and we see as new components appear and as they merge together. So there's one component which appears here and stays alive forever. And there's a second component in F that's born here, and here it dies because it's merged to an older one. So it's a half-open interval starting here and ending here. So this is the barcode of F, and the barcode of G looks something like this. There's another component born here, but then there's also something is born here, 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 and here. What's born here actually dies here, because only then it's merged to something older. So this gives me a bar like this, and then there's two smaller ones at this height. There's one bar at this height, there's another bar slightly longer, and then there's a third bar here. Okay? And now you can convince yourself that there is a correspondence between the barcodes. And so this theorem makes sure that when we have some data, we convert it into a function and then into a filtration. And we have some uncertainty either from sampling. Yeah? Sorry? You can. And this theorem here, I mean, I left out the precise assumptions because there's different variants of all these theorems. So there's a theorem. This theorem was originally proven for functions on triangulated spaces. And I think there was some assumption about tameness of the function. So the function should actually be linear on some triangulation. And So this is exactly the kind of questions that people try to push after this first proof appeared, and that's one of the motivations for coming up with an algebraic version of this theorem, is trying to see how far you can push this kind of theorem before it eventually might break. And maybe you can ask again at the end of the talk, and I can say something about what's the kind of current limit of abstraction of this theorem. But I left out the precise assumptions for the theorems for the reason that it should somehow show what's the spirit of the theorems, and if you want to cite them or use them for your own work, then you have to read them up anyway. And the best place to get certified assumptions for the theorems is to read them in the papers. But I can tell you what's the level of generality. So right, if I remember correctly here, the assumption was that at every level the homology is finitely generated, and there's only a finite number of levels where the homology changes. So there's two kinds of finiteness assumptions, and I also will present theorems that are very general, but I try to make the proofs in an accessible way using some additional assumptions that simplify the proof strategy. But it's the same strategy that works in the general case with more technical pain in the ass. Okay, so let me give you an overview what this TDA using persistence is in the big picture, and how this whole thing that we have seen breaks down into smaller steps. So we started with a point cloud, which we considered as our data. So this is simply a finite subset of some Euclidean space, and we passed from that to a function, as I said before, by considering the distance function to this point cloud. So that gives us a function on R to the D. You could also take another function defined on any topological space. For the next step, passing from that topology, we construct a filtration. You can use the sublevel set filtration. You can also start here. If you have some other way of defining a filtration from a data set, that's also fine. It doesn't have to be geometric. We take this filtration, we apply homology. Now we get a persistence module of one parameter family of vector spaces. And finally, we apply the last step, which is essentially the structure theorem for these persistence modules, telling us telling us the intervals of the persistence barcode. I've been a bit sloppy about what the barcode really is in the beginning, but I'm going to be more precise now, telling you what's the right interpretation. And the point is, the persistence barcode appears in the structure theorem about persistence modules. It tells us how these persistence modules look up to isomorphism, and so that's the kind of algebraic perspective on persistence. And then what's interesting in this big picture is we are also interested in stability, and stability means that we have four steps here passing through 5 different branches of mathematics, and the 4 steps are all, it can be considered as one Lipschitz function. So we have a metric on the point clouds, that's the Hausdorff distance. We have a metric on the functions, that's the one coming from the supremum norm. And we have metrics for filtrations, persistence modules, and also for the barcodes. And you see, I didn't mention this, maybe I will have time to come to this point at the end of the talk. The barcode can also be interpreted as a diagram of, in a certain category, the matching category. And you have the same indexing by the reals. So here we have 3 diagrams indexed over the reals, and we use the same notion of distance for such diagrams, and that's the interleaving distance that I will define in a moment. Okay, so let me say something about the assumptions on the filtration for the proof I'm going to give. We assume that the filtration is a filtration of simplicial complexes, and that every simplex, so the filtration grows simplex by simplex, so only one simplex appears at a time. So the filtrations we start with an empty complex, and then we have some complex K1 sits in K2 and so on, and we have the assumption that every complex Ki is the complex Ki minus 1 together with a new simplex sigma I. Okay, so that's what I call a simplex-wise filtration. And it's just to make some arguments slightly easier, and it's also the assumption that's required when you do computations, because then you have to order everything. Even though the way that your data gives rise to a filtration does not necessarily satisfy this assumption. The example that we have shown is filtrations coming from Delaunay triangulations, and there is a theorem saying that these filtrations grow in a structured way. They grow in clusters, so they grow in groups of simplices that have a common phase and a common cophase and intervals in the phase posted. So there's some structure, but they appear in chunks. There might be several simplices appearing at the same time, and both for doing simple proofs and for actually doing computation, you have to break ties between these. Okay, so this is my assumption for the filtrations. The other, maybe you have noticed this. The other change I made here is now I'm indexing by natural numbers instead of reals. Before I had the real numbers. So I make the assumption that that I can actually write my filtration, which is given in this picture always as a filtration index over the reals. But I can make the assumption that I can present a refinement of that filtration, and I can give you a order preserving map from the reals into the natural numbers. So this is my posit category of the reals, and this is my posit category of the naturals, and then I go from this to top, and that means I can I can present you the filtration that I want to work with by factoring through a filtration that's actually what I'm going to assume in my proofs and what's actually used in the computations as well. So and it's not difficult to do that. All you need to do is you look at how new simplices appear in the filtration. That gives you partial order on the simplices. You extend it to a total order, and you enumerate according to that total order. It's always possible if you only have a finite number of simplices, just to make sure this is how I resolve the formal mess of talking about something real index, but I want to often assume that I'm working with natural numbers as indices. Okay, so I assume what I'm given is a real index filtration, but I may simply, without loss of generality, assume an indexing by naturals. Okay, and that turns out to be very convenient. And maybe I can extend this diagram here to something larger. Maybe I start again. So what I want to do is we are given a filtration. Here's my re-indexing. I also want to assume that my topological spaces can actually be represented by simplicial complexes, and maybe up to homotopy equivalence. There's a where the geometric realization is somewhat homotopy equivalent to the actual topological spaces. So I can consider a commuting diagram of functors here. This is my filtration. This would be my working filtration, right? I have a filtration of topological spaces here. I have a simplicial filtration indexed by n. This is my re-indexing map, a poset map. This would be geometric realization, or the other way, maybe the nerve functor. And then in the end, I want to apply homology. So I can do either singular homology, or I can do simplicial homology, and all of this should commute. So this is maybe a picture to summarize what the different pieces are that enter this construction. Okay? So I think this is a good moment to take a break of 10 minutes, and then we come back to persistence models and the structure. So I said something about filtrations. I want to say something about persistence modules and persistence barcodes as well. So by the way, the first remark about persistence modules is what I just said is simply for presentations of the proof during this lecture. This is not necessary for the theory, but it will help in giving simpler proofs. So the persistence modules we're considering in general are really diagrams of this kind. I don't make the assumption that I can factor them through an indexing by natural numbers in general, but I'm making the assumptions today. And I'm making another assumption. I'm making another pair of assumptions actually. And the second assumption I can only really motivate after I've talked about barcodes. So here the assumption is all vector spaces. So I have a diagram, let's say M is my persistence module. It's a one parameter family of vector spaces. And I have connecting maps between every pair of indices. And I assume that all vector spaces MT are finite dimensional. Okay. That will be important for the structure theorem, which tells us what the meaning of this persistence barcode is. So first I want to say a persistence module is called indecomposable if I can't write it as a direct sum of other persistence modules as a non-trivial direct sum. So persistence module is indecomposable if it can't be written as a non-trivial direct sum. And using this notion of indecomposables, we have a structure theorem for persistence modules, and it's essentially the Krull-Schmidt theorem, Krull-Schmidt-Remak dt. in the case of persistence modules indexed over n. And then since we are with persistent homology, we're interested in R-indexed persistence modules. Crawley-Bovey gave a proof for the theorem in the case of real indices. I think it was 2015 for persistence modules index over R. And here the assumption is finite dimensional at each index. So, and the theorem says any persistence module can be written as a direct sum, is a direct sum of so-called interval modules. That's where the intervals in the barcode come from. So an interval module looks like this. In the case of natural number indices, you start with zeros, and then you, at some point you have a copy of your field. Then that goes on for a while, and eventually it may or may not go back to zero again. It may also stay the field forever. So there's a certain interval of indices over which the persistence module has support, and whenever you have a pair of those indices, then there's an isomorphism connecting the two copies of the field and nothing else. So it's a very simple structure, and every persistence module is simply a stack of these. So it's described, the persistence module up to isomorphism is simply described by knowing what the support of these intervals, of these interval modules is, right? So, and that's our interpretation. The support intervals describe the isomorphism type and the collection of those intervals is the persistence barcode. So the persistence barcode is really a property of the persistence module. It doesn't have much to do with homology or anything else up above in the pipeline. It's really something that describes in a combinatorial way what's going on here. So maybe it's important to, in order to get some intuition, to think about what this means in the topological context. I mean, one thing to point out is the theorem says we can find a direct sum of interval modules. It also says, I haven't written this here, the I should say in an essentially unique way. So the barcode is always the same. I can find different decompositions, and that's also important from a practical perspective, because when people come to us and ask us for what's the feature that I see in this barcode, I can't tell. I can only tell you that there is I can give you a cycle that represents this feature, but it's not by no means unique. I can also give you a very different cycle in some cases. In other cases, I can really give you only one cycle, but that really depends on the situation. But what I know from this theorem is, in general, the decomposition is not unique. So not only the non-uniqueness of homology, of cycles in the homology class, but also the non-uniqueness of how I decompose the whole picture into small individual features. This is it depends on how I perform the computation, what kind of representatives I get here. And this is important because I think that's a very common request that we get from application or people trying to do applications there's always the expectations that these features can be nailed down precisely, and that's just not the case. So this can be decomposed in an essentially unique way, and that at least guarantees us that the barcode is well defined, and then we always have the same description of the structure of the persistence module. Some other remarks here. So there's a correspondence between persistence modules indexed over the naturals and finitely generated graded modules over the polynomial ring for the corresponding field. And that's why I claim that this theorem has been known before, even though people haven't really talked about persistence modules. But this correspondence has been pointed out by Somarodian and Carlson. So corresponding to finitely generated graded modules over the polynomial ring over your field. And here the index in the persistence module corresponds to the polynomial degree in this ring and in the module, in the graded module. And that means that the structure theorem for such modules translates into the statement that I made here. The other remark I want to make, this is another assumption I mentioned before I wanted to make. When I apply persistent homology to a filtration that's simplex-wise, then only one simplex appears at a time, and then I take the barcode, then as a result, at every index something is born or something dies. And in particular, all the intervals have unique endpoints. Sorry, that's if the filtration is simplex-wise, then intervals have unique endpoints. Okay, and that's something that will be helpful for intuition and also for simpler proofs. So I want to go to the notion of interleavings now, and the motivation here is again by what we've seen in the stability statement before. We have two functions, f and g. The functions are delta apart, and we write f index t, capital F index t, for the t sublevel set of f, and similar for g. And then we can write a diagram that has this kind of zigzag shape that we have seen before. So a t sublevel set of f includes into a t plus delta sublevel set of g. So that's what we call a delta interleaving. And we call, if you take this viewpoint of filtrations as diagrams, then the maps pointing downward are natural transformations of between the filtration f and the filtration g shifted by delta. But we see a natural transformation here. That's the kind of class of morphisms of persistence modules that we consider. So one way to say this is interleaving of two filtrations consists of two morphisms between the two filtrations shifting degree. Okay, and now so we have two morphisms that make up an interleaving. They can be thought of as approximate isomorphisms. It's like an isomorphism, only shifting degrees. When you go back and forth, you end up at the same place as before, only shifted by 2 delta. Now I can take an interleaving of filtrations, and I apply homology. That's a functor, so all the commutativity is preserved. That means I immediately get an interleaving of persistence modules. So filtrations being delta close, it directly implies that also the persistence homology is delta close. So that kind of stability we get for free just by making use of the fact that essentially we're using the same kind of distance between filtrations and between persistence modules. Okay, so that was one step in the pipeline of stability steps. This is a very easy step, by the way. Going the Hausdorff distance corresponds to the L infinity distance of the distance functions, and this step is also easy. That's something I just remarked in passing on the slide we've just seen. And so this is also an isometry going from functions to the interleaving distance between the sublevel sets. It's an isometry. So if we take the L infinity distance here and the interleaving distance. The interleaving distance, I should say that we consider an interleaving diagram as this, and the interleaving distance between two diagrams F and G is simply the infimum delta where you can find an interleaving. So this determines the notion of distance that we applied to the last 3 steps. And this step, as I said, is simple because we just apply a functor. Of course, that maybe brings up the question, will the last step also be simple? Can we also just apply a functor to go from vector spaces to this category? That turns out not to be true. Maybe I'm not sure if I will have time to cover that, but before I want to show a way how to prove stability in a way that studies the structure. Okay, so as I said, maybe this just a short illustration of interleavings in the geometric case. So you have a picture in mind. Here's a point cloud that we've seen before. Here's a second point cloud that's nearby in the Hausdorff distance. And now geometric interleaving simply means that the red point cloud is included in the blue one, in the balls union of balls around the blue points, which is again the converse is true for the opposite pairings, and we have this kind of nesting in ever including balls. So this is the kind of geometric picture of the interleavings. Okay. And so this is the algebraic variant of the theorem that we are going to prove. If we have 2 persistence modules and we have a delta interleaving, then we can get a delta matching of their barcodes. And again, this means that matched intervals have similar endpoints within distance delta, and the unmatched ones have to have a short length. Right. The way we're going to prove this is by first studying the structure of submodules of a persistence module. So as we have a structure theorem for persistence modules themselves, we also have one for submodules that tells us that if one persistence module is a subspace of another one at each index. That's what we call a persistence submodule. And then we have a strong restriction in what the barcode of this submodule can look like. And the theorem goes like this. So it's about the structure of persistence submodules and quotients. Okay, so we have two persistence modules M and N. And we have a morphism from M to N. So a natural transformation. I have a map from MT to NT at every index, and these maps commute with the maps within the modules M and N. And we assume that F is an injection. Then there exists, so maybe let me spell out what this means. We have the map FT, the maps FT making up this natural transformation, a linear map from MT to NT is injective at every index T. So what the structure theorem tells us, that for every bar in the barcode of N, for every interval in the barcode of M, let me draw a picture because the theorem is easier to see than to write down. If I have a bar in the barcode of M, then there is a corresponding one in the barcode of N with the same right endpoint and a left endpoint that's further to the left than that of M. So we could also have this. And moreover, there could also be an interval in the barcode of N that does not have a corresponding bar in M. But whenever I have one in the blue barcode for M, then there must be a unique one in N, and it has to be longer at the line to the right. For every interval in Bm, there exists a unique interval in Bn with same left, right, and smaller left endpoint. Okay. And dually, I have a statement not for submodules but for quotients. So if I have surjection here, then the situation changes. I get the same left endpoint here and a larger right endpoint. So the situation is symmetric. And the proof is the same, and the the proof is not too difficult, and it's also very intuitive. So I can give you a sketch in pictures. We consider a bar in the barcode of M. We have a morphism of persistence modules, a family of linear maps that are compatible with shifting indices. And so this bar is mapped to a linear combination of bars in N, Bn, but we can't map them to any bars. For example, we can't map to this bar because that would violate the commutativity condition. Because I go from here to here and then I go within the module shifting degree, I would end up here. But if I go from here to here and there's nothing, 0, and I would end up at 0 here. So those bars are excluded. And also such a bar would be excluded because I would go through 0 here but not here. So I only hit bars that overlap my blue bar to the left on both endpoints, right? So let me summarize this. A bar I of the barcode of M is mapped to a linear combination of bars of Bn, and the naturality the assumption that my morphism is a natural transformation enforces that those bars overlap my interval I to the right. Yeah? At both ends. So this is not allowed, this is not allowed, but those are okay. And yeah, of course, this wouldn't be allowed either. And the other, so we have said nothing about submodules here, about injectivity. So this is just about how do morphisms of persistence modules look like. Now we assume that F is injective, and that tells us one of the bars that we map to has to die together with the blue one. Very romantic, right? So there must be one, it has to, I wrote this wrong. Those I overlaps those bar to the right. So I sits to the right, the red bar sits to the left. So let me fix it this way. Sorry. Okay. One of those ends together with I. Because otherwise, I mean, if we just took these two that I started with, then the map at an index that goes beyond the support of those bars would not be could not be injective anymore. I need to have something to keep the map injective, right? So it starts to the left. It's longer than this bar I, but it has to die together with I. So that's really the reason why we have this structure, and that's almost all we need, right? We have this structure for submodules. We have the dual picture for quotients, and that already can get us stability in another simple pictorial proof. Before going to stability, I want to introduce the notion of induced matchings. So, sorry, how much time do you have? Till 4, okay. So, first observation is this theorem gives us a matching of barcodes, because I have a unique, for each bar in M, I have a unique bar in N. I have an injection of barcodes that works for surjections, and it works for injections. Now, if I have an arbitrary morphism of persistence modules, then I can simply split the morphism by an epimorphism followed by a monomorphism, and that induces a matching between the barcodes of M and N. So for any general morphism, we consider the splitting from M by an epimorphism to the image of F, and then we have a monomorphism, an injection into N. And so we have from this structure theorem, need more colors. Let's say this is my one bar in my barcode of M. And this is a bar in the image. And since this is the first map is an epimorphism, the left endpoints are aligned, and the bar in M is longer. And then I have wrong color. Then I have a bar in N, and it's aligned to the right. And this gives us a way of getting a matching of barcodes from a morphism. Okay? And in particular, we can apply this to interleavings. And if we have an interleavings, we said this is essentially given as a pair of morphisms back and forth, shifting indices. And maybe let me leave the structure theorem here. And now I'm gonna tell you how to see that the induced matching actually satisfies the 2 points that we want to show in this theorem, that the matched intervals are similar and unmatched ones have to be short. Okay, so this is the proof of the algebraic stability theorem. We have an interleaving MT, and here is NT minus delta, here is NT plus delta, and there's this maps back and forth in a zigzag way. And we have this for all t. So let's collect some facts about this, right? So we know that the image, let me call this map here little n index t minus delta, t plus delta. This is the internal map of the persistence module. We have a chain of submodules. The image of this internal map, t plus delta. I'm talking only about vector spaces here, but everything I'm saying applies to all indices, so it's really a statement about persistence modules. This is just to simplify the picture here a little bit. So I have the image of this map, which is a submodule or a subspace at index t of the image of, let's call this interleaving morphism ft. And so this is a subspace of the image of ft, as you can clearly see from this picture, which is a subspace of nt plus delta. So this is some subspace relations I know. And then I also know a certain quotient space relation, namely mt is a quotient space of the image of ft, right? And so let's put this in a picture, starting with a bar from n. And you can compare this to these two pictures. So one other thing I need here is this same bar shifted by delta to the left, because that's appearing here. Adding delta to the index is the same as shifting to the left. So let me write this as n subscript bullet plus delta. This is the barcode of the shifted persistence module. That's one guy. And then I have this relation here. So the image of f is a submodule of that. I don't know where it starts, but it ends at the same point. And then I have another one, which is, let me call this the delta erosion of this bar, or the delta erosion of n. So this is simply the image of this guy. So this starts delta after my original bar, and it dies delta before. Okay? So now we see already that we have nailed the down the left endpoint of this blue bar of image of f within a range of plus minus delta around the original endpoint. So there's delta to the left here, can go delta to the right. And this endpoint here in question sits somewhere here. But this is exactly by the second observation that we made here. Sorry. This is exactly the endpoint, the left endpoint of some bar in BM. Okay? So using the morphism F, we constructed this induced matching, and the induced matching should correspond to the colors I've chosen here. BM, image of F and N. So this was, well, this was my original bar, and then I shifted to the left by delta. And then here's the induced matching, defined using the image of F. And from this argument, you can see that the endpoint is actually constrained to an interval of length, like plus minus delta around the corresponding endpoint in M in N. So this is the argument that tells you how to nail down the left endpoint. Of course, a dual argument applies to the right endpoint because we have all these structurally dual statements, and so that's one way to prove the stability of persistence barcodes. Okay, I think I'm over time already, so thanks for your attention.
Questions? So is this one, doesn't it also lead to the result of this isometry relation between the leaving and the...
I mean, this is one part of the isometry, right?
one
So,
half of it.
yeah, so, right. So one, this isometry statement says that the converse to this theorem is also true. When you have a delta matching of barcodes of two persistence modules, then there exists an interleaving. And the other direction is actually much easier because you can simply, the barcode describes a persistence module, and the matching describes a certain pair of morphisms between those persistence modules. You can construct them directly by mapping one bar exactly to the matched other bar. And so the converse direction is pretty much straightforward, and this direction is the one where it becomes hairy. Yeah. Uh-huh.
If you go the converse direction from this, you get different matching?
Yeah. Yeah, different interleaving in general, right? You're bending things a little bit when in general, yeah. And it also depends, I mean, the converse direction also depends on your choice of decomposition again, right? You know that you can decompose your persistence modules in an essentially unique way, but there are several choices, and the converse is essentially using some choice, whereas this direction here never makes an explicit use of a choice of decomposition. So, yeah. And even then, even if there are some cases where there is no decomposition that actually gives you the same result, if you go back and forth. If you're interested, I think I can show you an example. So it's really it's more than that. Yeah, there's some things are severely broken into pieces when you do this last step in stability. So, sorry,
In the beginning, you
yeah.
reconstructed the line with like plots with big balloons, small balloons, and yes, but some time ago.
Huh?
Are you aware of algorithm implementing that idea for, let's say, edge reconstruction?
I don't understand what exactly the idea is. I mean, you
construction to use this?
Yes.
For
Sorry,
you mean this picture for doing reconstruction?
no, you want with big balls. I mean, you have the line given by plots.
Uh-huh.
A bit later than that.
Later the shape,
was a
like a
problem.
semi-U shape.
Ah, yeah. Okay, sorry.
Yes, there was a problem with
This one.
if you only take one ball and only approximate that, you can't really get a good edge reconstruction.
Yeah.
And but taking two balls, you could actually get some predictable results.
Ah, yeah. Okay, I can tell you something. There, that's actually it's actually not so easy. I mean, somehow we don't have a nice reconstruction theorem. We only have this homological proxy, And it turns out that what you're asking for is now I know what I should expect. Can I get a geometric picture of that? And that turns out to be not possible in all cases, and actually even for point clouds in R3, deciding whether it's possible or not is an NP-hard problem. Which is, yeah, I mean, whenever something does not always work, there's a chance that it might also be NP-hard, and that's something we showed a couple of years ago. So it's not, I mean, it seems that it should be possible, but there's, I can show you an example, simple example where the kind of smallest example where a reconstruction is not possible. But yeah. Mm-hmm.
So again, this speech, I think one of the things that may go wrong that choosing or using the same delta around each point could make some cycles time for some other clues or phenomena like that. Namely, you could have at the beginning a crowd of points that are in some regions more concentrated,
Yeah.
and some other regions are more rare.
Yeah.
So, is there some way to differentiate the choice of delta for whose use different?
You should ask Yusu. She's working on methods for this kind of problem.
This is basically you're growing a uniform force around every point, but you can also think that you grow them adaptively. That's a real question.
So that
They're limited this area along those lines. Yes, there's some results we have some when the points are sampled from nice manifolds. Okay, not arbitrary complex sets in RD. From nice manifold embedded in RD, there's some results that you can grow scalable and then still reconstruct the homology. I can tell you more later. All right, if there's
Thank
no
you.
more questions, let's thank Uli again and also